Today's topic under discussion is simulated annealing in artificial intelligence. This is an optimization algorithm. It is derived from metallurgy annealing process. It can solve complex AI problems. Simulated annealing is a probabilistic optimization technique. What are the principles behind simulated annealing? High temperatures allow exploration. Gradual cooling helps settle into global optima. Allows probabilistic acceptance of worse solutions to escape local optima. How simulated annealing algorithm works? We'll be starting with initial solution and temperature. We'll be computing the cost. We'll be modifying to create neighbors. We'll be using probability to decide to accept or reject. We'll be decreasing the temperature and repeat until the stop condition is reached. What are the key features of simulated annealing? It is stochastic exploration. It approximates global optimum. It has generic applicability. It is sensitive to cooling schedule. What are the applications in artificial intelligence? Many combinatorial optimization problem. For example, traveling salesman problem, scheduling, neural network training, feature selection, game AI and robotics, computer vision. What are the challenges of simulated annealing? It requires careful cooling schedule. It needs parameter tuning. It converges slowly in some domains. What are the current research trends? It's a hybrid method used along with GA, PSO, RL. That is genetic algorithms, particle swarm optimization, reinforcement learning. It is used in deep learning hyperparameter tuning, used in parallel and distributed simulated annealing, used in adaptive cooling schedules. These are a few of the papers which I referred, and one of the papers, Van Laarhoven and Arts, I'll be referring now to go further about simulated annealing discussion. So, we know the importance of optimization, right? We are always in the search for an optimum function of a continuous variable. Many large-scale combinatorial optimization problems cannot be solved to optimality because the search for an optimum requires prohibitive amounts of computation time. Here the example of traveling salesman problem is given of more than 318 cities. 10 minutes of CPU time only came after years of research for just one 318 city instance. So instead of that, people tried approximation algorithms or heuristics where there is no guarantee that the solution found by the algorithm is optimal, but for which polynomial bounds on the computation time can be given. Let us formulate this combinatorial optimization problem with a pair R, C, where R is a finite set of configurations called as configuration space and C is a cost function. It assigns a real number to each configuration. Okay. What is optimum C? The lower value of C. The lower, the better. What is the problem now? The problem now is to find a configuration for which C takes its minimum value. That is an optimal configuration IO satisfying C optimal is equal to CIU, which is equal to minimum of CI. Coming to simulated annealing. It is based on the analogy between simulation of annealing of solids and the problem of solving large combinatorial optimization problems. In physics, what annealing indicates, it's a physical process in which a solid in a heat bath is heated up by increasing the temperature of the heat bath to a maximum value at which all particles of the solid randomly arrange themselves in the liquid phase, followed by cooling through slowly lowering the temperature of the heat bath. In this way, all particles arrange themselves in the low energy ground state of a corresponding static lattice, provided the maximum temperature is sufficiently high and the cooling is carried out sufficiently low. So starting off at the maximum value of the temperature, the cooling phase of the annealing process can be described as, at each temperature value T, the solid is allowed to reach thermal equilibrium, characterized by a probability of being in a state with energy E given by the Boltzmann distribution. So here, this is the formula for that. Probability of E is equal to 1 upon ZT, where ZT is a normalization factor known as partition function depending on the temperature T. Kb is the Boltzmann constant, exponent of E divided by kBt negative. The factor exponent of minus E divided by kBt is known as the Boltzmann factor. As the temperature decreases, the Boltzmann distribution concentrates on the state with lowest energy, and finally when the temperature approaches zero, only the minimum energy states have a non-zero probability of occurrence. If the cooling is too rapid, that is, the solid is not allowed to reach thermal equilibrium for each temperature value, defects can be frozen into the solid and metastable amorphous structures can be reached rather than the low energy crystalline lattice structure. Furthermore, quenching, the temperature of the heat bath is lowered instantaneously, which results again in a freezing of the particles in the solid into one of the metastable amorphous structures. To simulate the evolution to thermal equilibrium of a solid for a fixed value of temperature T, Metropolis proposed Monte Carlo method. Okay, so this was a brief about simulated annealing, physical process, actual process. Applications we have seen, but here the applications being mentioned are computer-aided circuit design and many more as mentioned. Image processing, code design, neural network theory, and so on and so forth. So this is a brief regarding simulated annealing, and here as mentioned I have used this Van Laerhorn et al. Paper, which was a Springer publication. Thank you so much.